Welcome to this video on taming high-frequency noise in buck converters. We will cover a practical guide to RC Snubber circuit design and implementation. In buck converters, rapid switching generates significant high-frequency noise called ringing. This ringing is a common source of electromagnetic interference, affecting compliance and system performance. You can see the oscillation superimposed on the switching waveform. The culprit behind the ringing is parasitic inductance and capacitance present in real-world circuits. When the switch turns on or off, energy stored in these parasitic inductors resonates with the parasitic capacitance, leading to the high-frequency ringing and subsequent EMI. An effective solution to suppress this high-frequency noise is the RC Snubber circuit. This network, consisting of a resistor and a capacitor in series, is placed between the switch node and ground. Its purpose is to safely dissipate the resonant energy that causes ringing. The snubber dissipates resonant energy in a two-step process. In phase 1, the high side switch is on, and energy charges the snubber capacitor. In phase 2, the low side switch is on, and the stored energy discharges through the snubber resistor, dissipating energy as heat. Energy dissipation introduces a power loss, which impacts overall efficiency. The total power dissipated by the snubber resistor in each switching cycle can be calculated using the formula shown. Since parasitic values are unknown, a practical, empirical method is required to find optimal snubber values. This 8-step process involves making direct measurements on the actual circuit to determine the optimal RSNB and CSNB values. Step 1 is accurately measuring the initial ringing frequency. Use a high-bandwidth probe and connect the probe tip directly to the switch node with a short ground connection to avoid introducing additional inductance or capacitance. Steps 2 and 3 determine the parasitic capacitance. Connect a test capacitor and adjust its value until the ringing frequency is halved. The total parasitic capacitance is then calculated as 1/3 of the added test capacitance, as shown in the example calculation. Steps 4 through 6 calculate the remaining values. Step 4 uses the resonance formula to find the parasitic inductance. Step 5 calculates the characteristic impedance, which determines the optimal damping resistance. Step 6 sets the snubber resistance equal to this impedance. Step 7 involves selecting and tuning the snubber capacitance. Start with a value 1 to 4 times the calculated parasitic capacitance. Test standard capacitor values in this range and observe the waveform. The example shows 680 picofarads provides the best balance of performance and efficiency. Step 8 is to calculate the power loss and select an appropriate resistor. Use the power loss formula with your chosen snubber values. Select a resistor with a power rating at least twice the calculated maximum power dissipation for reliability, as shown in the high voltage consideration. The result of this systematic, measurement-based approach is a clean waveform. By installing the optimized snubber, the disruptive high-frequency ringing is eliminated, transforming the noisy waveform into a crisp, clean, square wave. Finally, remember that an empirical, measurement-based approach is key when parasitic values are unknown. Always balance performance and loss, and verify performance across different operating conditions to ensure a robust design. You now have a repeatable methodology to systematically solve switch node ringing.